Let's start with this standard normal random variable. It is often known as the Gaussian random variable. It will have the PDF of this kind. So the formula for this PDF, so we have this random variable x, and this random variable x is a Gaussian random variable, and it will take the value little x. So this little x can be any value from minus infinity to plus infinity, and it will have the expression like this: 1 divided by root 2 pi e to the power minus x square divided by 2. Let's first try to understand this expression, or let's have a look at the plot of this probability density function. So this, in this PDF we have this term, that is the constant term, and we have this negative exponential term, and in negative exponential term we have this x square divided by 2. So the plot of this x square will be a simple parabola centered at or symmetrical around this point, that is x is equals to 0. Now if we take the negative exponential of this, that is this term, so it will be maximum. Since it is a negative exponential, it will be maximum when this value is at minimum. Let me repeat one more time. Since it is a negative exponential, the whole expression will be maximum when this exponent term will be at its minimum value, and when it is minimum, when x is 0. So then it will have the maximum value when x is 0, then x square will be 0, and this expression will be 1, right? And it is exponent, so from here it will start decaying, right? And it will decay, and this will be also symmetrical because we have the this x the power term, that is x square. So whatever the value you will take x is equals to 1 here, the same value you will get for x is equals to minus 1, because minus 1 chi square will be 1. So it will be symmetrical around this point, that is x is equals to 0. So this is, you can say, approx or the rough sketch of this probability density function. So you will have the idea that this PDF will have a plot that will look like something like a bell curve, right? And it is symmetrical around this point, that is x is equals to 0, right? So now if I ask you what will be the expectation of this Gaussian random variable, what will be the expectation? The expectation you can see from the plot that it is symmetrical, the probability distribution is symmetrical around this point, that is x is equals to 0. So the expected value will be 0. And if you want to do it using the PDF, you can do that. So we know how to find the expectation of a random variable. So we just need to integrate from minus infinity to plus infinity, and we need to integrate this expression 1 divided by root 2 pi e to the power minus x square divided by 2 dx. If you look at this expression, so this function is a odd function. How? If you put minus x, what you will get is minus times of fx, right? So this expression is a odd function. So once you will put x is equals to minus x, so x square will be again the same thing. Here we will have minus x, so f minus x will be minus times of fx, so that means this function is an odd function, right? And also we know the integral of the odd function is 0, right? So the expectation of this random variable would be 0. Now let's try to find the other quantity, that is the variance of this random variable x. So the variance would be 1. We can also find this variance, but in order to find, you need to also, so first of all, how do you find this variance? So we can use the standard formula of the variance. So that would be the expected value of x square minus expectation ka whole square, right? We know this expectation, that is 0. We need to find the expected value of this x square. We can make use of the expected value rule and we can find, so that would be integral from minus infinity to plus infinity x square, and the PDF is 1 divided by root 2 pi e to the power minus x square divided by 2 dx. You can find the integral of this kind using by part, but what I am going to do, it is better to remember few results, and those results will always help you to find this kind of complex integration. So let me first of all give you, so I know the integral from 0 to infinity x square e to the power minus x square dx. So this is a very famous integral in probability theory. You will find many times this integral, so you can directly remember this, or otherwise what you can do, you can find this integral using the integration by part. So the result of this integral is root over pi divided by 4. So I am going to make use of this integral while finding the variance of the normal or the Gaussian random variable. So you see, here we have x square divided by 2, here we have x square, here we have x square. So but we need to make in this form, right, so that we can directly use the result. So somehow we need to manipulate this, and if you look at this function, this is a even function, right? So this integral will be, we can now take the integral from 0 to infinity, and that will be 2 times, right? And how why it is even function? So f of, if you consider this as a function fx, then try to evaluate this f of minus x, then it will be f of x, right? Because if you put minus x, then x square will be again x, minus x square will be again x square, and here again minus x square will be x square. So overall this function is a even function, so we can integrate it from 0 to infinity, and total integration will be 2 times of 0 integral from 0 to infinity, right? So x square divided by 1 divided by root 2 pi e to the power minus x square divided by 2 dx. Now let's, so we have achieved this one, right? Now let's try to bring this, so we have nothing here, we have just x square, so we need to somehow make this t square. So this, there should be nothing, no other terms here. So we can simply, what we can do, we can simply assume that the x divided by root 2 is equals to t, or yes, then from here dx will be root over 2 dt. Right? Now we can substitute 0 to infinity. So what will be x square? So x square will be 2t square, right? So we can put here 2t square, and this will be a constant term, so let's put it outside of this integral. Into e to the power minus, this will be t square, right? Because we have assumed this. So this will be t square, and in place of the dx we will have root 2 dt. So we can put root 2 outside of this integral, and here we will have dt. Right? And even we can put this 2 outside of this integral. Now we can directly make use of this result. So this is what we have here, right? So this, the value of this integral will be, so 2 times root 2 into 2 times 1 divided by root 2 pi into root pi divided by 4. So I think all the terms will get cancelled. This 4 will get cancelled with this 2. This root pi will get cancelled with this root pi. So everything will get cancelled, and you will have this 1. So the variance of the normal random variable is 1, and the expected value is 0. And we have the shorthand notation for this standard normal random variable, and the shorthand notation is we write like this. So this is standard normal random variable with the mean 0 and with the variance 1. So this is what the standard normal random variable or standard Gaussian random variable. Anyone, if anyone is saying standard normal random variable, that means you need to consider this PDF, and it will have the 0 mean, and the variance would be 1. Right? Now let's look at the general Gaussian random variable or general normal random variable. It will have the mean some around, and variance it will have some other, any general variance. So if we have to write this in the shorthand notation, so this n stands for the random variable, that is the normal random variable, and it will have the expectation or the mean some around mu, and it will have some variance, that is sigma square. The PDF of this general Gaussian random variable will have the form that will look like this. Again, this x is a general Gaussian random variable, and it can take the value, any value from minus infinity to plus infinity, and it will have the PDF expression will have of this kind: 1 divided by root 2 pi e to the power minus x minus mu square divided by 2 sigma square. So this whole term is the exponent of this e, right? So if we have to look at the plot of this, so it will be kind of similar, but so this is the constant term, right? And we have this exponential term, and the exponent is this expression. So if you look at the plot of this expression, so again this will be a parabola, right? X minus mu whole square, that will be a parabola, and now this time it will be symmetrical around x is equals to mu. Right. So this is x minus mu square divided by 2 sigma square. Now if you take the negative exponent of this expression, so when this will be maximum, when this term is minimum, because we have in front here negative, and since due to this square, when this will be minimum, when we have at x is equals to mu, so this has to be 0. So when it will be 0, when x is equals to mu, so that means this will be maximum at x is equals to mu, right? And since it is negative exponent, so it will start decaying from here, and it will be symmetrical around this point, right? Because we have this x minus mu ka whole square. Again it will have the shape of the bell curve, right? And it will be symmetrical around this x is equals to mu. So from here we can directly write what will be the expected value of this general Gaussian random variable, that will be mu, right? Or you can find the using the how we have found this expected value, and the variance would be the variance of this general random variable, that will be sigma square, right? The point to note here that these two parameters controls the shape or the size of this bell curve. So depending upon this value of mu, so this bell curve will get shifted, right? If mu is here, then bell curve will be symmetrical around this point, and depending upon this sigma, you will have different shape of the bell curve. So let me explain this to you. So now let's say how we can see that how sigma is affecting the shape of this curve. If we consider sigma to be very small, right? So if we look at this parabola, and if we consider this sigma very small, then this term will be very large, right? Since this sigma that is very small is in denominator, then this overall term will be very large. If sigma tends to 0, then this whole term will tends to infinity, right? So overall point is that if sigma is very small, then this quantity would be large even for the small value of x. So this parabola would itself be a narrower parabola, right? Because even if you take the small value of x, the this expression would be a large, right? And it will be a narrower parabola. And here, since sigma is small, for a small value, even if for a small value of x, it will decay fast, right? So now the decay rate would be fast. So the overall bell curve would be narrower than the sigma that we have considered as a large sigma. And even this reflects here that we have found the variance is sigma square. And what is variance? Variance is expected value of the square distance from the mean, right? So the variance overall controls the how much the distribution will be spread, and it turns out to be sigma square. So overall this sigma square or the sigma controls that how much narrower this distribution would be, or how much spread out. So point is, depending upon the value of this sigma, the shape of the overall distribution would be more spread out if sigma is large, and if sigma is small, then the distribution or this curve will be narrower, right? So most of the probabilities, if sigma is too small, then most of the probabilities will lie in the vicinity of around the expected value, and if sigma is small, if sigma is large, then this curve will have the more spread, and the probability will be more spread out throughout the possible values of x. Okay, now let's look at one more important thing about this normal random variable. Let's say if you have our normal random variable, and this has mean mu and variance sigma square. If I ask you, let's first of all take the linear function of this random variable x. So this is a normal random variable, and what we have done is we have applied some linear function to this random variable x, or a linear operation to this random variable x, right? So let's call this as a y, this random variable y. So once you do the linear operation, so what you will be doing? So you have this bell curve, right? This random variable x, where the mean is sigma square, mean is mu, and the variance is sigma square, right? And if you do some linear operation, what you will be doing? So overall you will be either shifting this mean, or maybe also you will be also scaling the curve, right? So maybe maybe after doing the linear operation, you will have mean somewhere around here, and the curve will be more narrower than this original. But the overall point is that again this distribution will be a normally distributed distribution, right? So this y, that is the linear function of a normal distribution, will also be normally distributed. So this random variable y will also be a normal distribution. What will be the mean of this random variable y? Using linearity of expectation, the expected value of a random variable y, that is a linear function of x, would be a times the expected value of random variable x, that is mu, plus b. What will be the variance? So we have seen variance of this random variable y. So using property, the variance would be a square times variance of this random variable x, that is sigma square. So this random variable y will be normally distributed with the mean a times mu plus b plus a square, and the variance would be a square sigma square. So the overall point is that the curve or the shape of the distribution or the PDF is still preserved, right? Even if you are doing some linear operations to a normal or a Gaussian random variable, right? So linear function of normal random variable. We will see more about this Gaussian random variable in next lecture. Thank you.